Okay, so this is Generalized Linear Models with examples in R, Chapter 4, and we're on question 4.4. We are going to do a lot of things with the score function and the log likelihood and deriving different statistics such as the Wald statistic and score statistic for a normal distribution. Okay. So the question tells us that the normal distribution is given by this expression. Get the whole thing in there. That expression right there. Okay. Where sigma, and therefore sigma squared as well, is greater than 0. So that should be apparent, right? Variance is always positive, and it can go all the way. Well, it can go up to infinity, really, and that mu can be any value, any real value, I guess. So throughout this question, we are going to be considering the mean. We're doing things with the mean, estimating the mean and the different statistics, under the assumption that the variance is known. Now, that's not usually going to happen, but when you're trying to estimate two parameters, it's obviously a little more complicated. And so I think this question is just trying to get us to focus on, on one parameter. Now, having said that, I also go through and I do the same, I do all of these questions also for sigma squared, assuming that mu is known. Again, that's, what I'm doing here is kind of an artificial situation, right? You're generally not going to know either parameter, although in my mind, knowing the value of mu and trying to estimate sigma squared is probably a more realistic situation, but what do I know? Okay. So let's go through this. This is just very, very math heavy, and so I encourage you to go to the Colab sheet, and step through everything, and I'll just kind of walk through a couple things here in the video. Okay. So question 4.41, or the first part of this whole question, is we want to determine the log likelihood, or the likelihood function and the log likelihood function of the normal distribution. Okay. So the likelihood function is just taking our probability distribution over all observations, and assuming that the observations are independent, then this is just the product of everything. Okay. So if we take our expression for the normal distribution and just take the product over n observations, we get here, and then we can do some simplifying basically to where we come out with this expression here. Okay, and so of course, that's our likelihood function. And of course, the log likelihood is then just taking the log of that guy. Okay, and so that's what goes on here. Now, it's worth really understanding why we're typically working with the log likelihoods in this kind of a situation. One is because the log likelihood is just, you're just adding and subtracting terms instead of having to multiply terms, and so adding and subtracting is easier than multiplying and exponentiating things, etc. And insofar as what we're concerned with is a point estimate, okay, like the most probable value of this or that parameter, well, the most likely value of a log likelihood is the same most likely value of just the likelihood. And so because log likelihoods are easier to work with, and they give us the same answer in terms of a point estimate of the most likely value, then we just work with log likelihood. Now, if we were in a different context, like a Bayesian context or something, that becomes a little bit of a different situation, but we're not to worry about that here. Okay. So now we're going to find the score function, and the score function is just the derivative with respect to the parameter of interest, here mu, down here sigma squared, of the log likelihood. Okay. So all I'm doing is taking the derivative of this guy with respect to mu. Okay, and ultimately we come out with this as the score for mu. Okay. Now I can do the same thing with sigma squared, but now I'm taking the derivative with respect to sigma squared, and I come out with this. If you're working through the math here, there's a little bit of a or something that often trips me up. So my parameter here that the parameter that I'm working with here is sigma squared, right? Which is just the square of sigma. Okay. Now where this can become a little bit confusing is where maybe you have the square of sigma squared or something like that, and then you're having to manage these exponents. But if you just remember that you could just treat this, you could just give that a different label, call it S or something, and then work through the derivation, then replace all of the S's with, sigma squared, and you'll come out with the right answer. Okay. So in the end, then, our score function, if we're to put it into a vector, right, would just be the gradient of the log likelihood over both parameters, right? So it would just be, the derivative with respect to mu, with respect to sigma squared, and it would be this guy right here. Okay. Now we're on part 3, and now we're going to find the maximum likelihood estimate. Okay, this is the point estimate I was referencing up here when talking about why we use log likelihood instead of the likelihood, right? It's just simpler to do, and they're the same value. Okay, so we're going to find the maximum likelihood estimate of mu, and I'm also going to do it for sigma squared. Okay, and the way that we do this is we take now our score function for the given parameter, and set it equal to 0, and then we just solve for mu, and then we call that mu hat, right? So if you go through those steps, you should come out with this, and this is just the basic arithmetic mean that we all learn. Okay. Now if you do that for sigma squared, right, same thing, right? So you just take the score function for sigma squared, set it to 0, solve for sigma squared, okay, and you come out with this expression right here. And this is really, really close to the very common expression that we use for an estimator of sigma squared, except for we usually use 1 over n minus 1. Okay, and I'm not sure if the book is going to go there or not. I'm sure that I've done this in other videos somewhere, but it turns out that that 1 over n is biased, and you can actually prove the bias. I'm not doing it here. But in other words, the MLE for sigma squared of normal distribution is biased. So anyway, there you go. Okay, so now we're going to find the observed and expected information for mu, and of course for sigma squared. Okay, so what is the observed information? Well, the the observed information is just it's just the negative derivative of the score function, right? So the score function was the first derivative of the log likelihood, which means that the observed information is the negative second derivative of the log likelihood. Okay, so if I just take the derivative now of the score function for mu, right, this guy right here. Okay, again, you can do it for yourself, but you come out with this. Okay, and now what is the expected information? Well, it's the expectation of the observed information, and here they end up being the same thing, I believe. I'm saying all of this as though I'm 100% sure that I have not made a mistake, but if you catch a mistake, please let me know. Okay. Now, similarly, for the observed information for sigma squared, again, it's just the derivative of the score function for sigma squared with respect to sigma squared. Okay. And so we go through, do all that, and we come out with this. And of course, what is the expected information or the Fisher information? Well, it's the expected value of this. And when you do all that, I believe you come out with an expression like this. This one or this one. They're all equivalent because this is, of course, an equation. Okay. Well, so that's all fine and good. But when we're doing these, when we're finding the information of something that has more than one parameter, there is also these cross terms, right? So for mu, right, when we were finding the information for mu, well, we took the derivative with respect to mu of the score function with respect to mu, right? Well, I could take the derivative of the score function for mu with respect to sigma squared, Okay, so that's these cross terms. Okay, and so there are also these cross terms here. Okay, and it turns out, I think in basically every instance, but I could be wrong, but that the second derivative with respect to the log likelihood in whichever order, right? Taking the second derivative with respect to sigma squared versus mu, or vice versa, comes out with the same answer. Okay, and so here, again, you can go through the math. Okay, but now notice here. So for this instance here, I'm taking the score function with respect to sigma and taking the derivative of that with respect to mu. Okay, and working through the math, and here it comes out to be 0. That won't always necessarily be the case, but here that is the case. And of course, the expected value of 0 is 0. Okay, and now I do it in the reverse order, and so now I'm taking the score function with respect to mu and taking the derivative with respect to sigma squared, right, and you come out to 0. Okay, so overall, then, the information matrices, so the observed information matrix looks like this, right? So that's the information for mu, for sigma squared, and then the cross terms. Okay, and of course, the expected information, is just that. All right. Okay, so now we're meant to find the standard error for mu, and of course, I'll do it for sigma squared. So the how do I want to address this? Okay, so the variance of our parameter is 1 over the information matrix, or it's the inverse of the information matrix. And so if I want the standard error, I would actually want the square root of the variance. And so that translates to the information matrix to the 1 or to the negative 1/2 power, right? That's the inverse of the square root of the information matrix, right? And so for mu, right, if you remember, that's our term for mu. I go 1 over the square root of that guy, and I come out with this, which again should be a very familiar expression for the standard error of mu. Doing the same thing for sigma squared. This probably is not as familiar looking, but this is what we get right here. Again, what I'm doing is I'm taking the square root of the inverse of the information, okay, to get the standard error. Okay, so now we come to the different statistics. So the Wald, the score, and the likelihood ratio, log likelihood ratio. Okay. And so all of this is just manipulating numbers. Okay. So again, so some things to point out here. So the null hypothesis here is that mu equals 0, and I'm coming up with a different null hypothesis for sigma squared, and I'm just saying that the null hypothesis is sigma squared equals 1. Okay. Again, I'm making that up, and so I'm doing the operations as though that's the null hypothesis. Okay. But this is the expression for the Wald statistic. Okay. I don't know what else to say about it, but we come out with this. Here again, 0 is representing the value of the null hypothesis here. So that's what the zeros are. Okay. In fact, I should have been more clear and put mu here and then substituted the 0, but hopefully you get it. Okay. And similarly for sigma squared. Oh, you know what? That should be sigma squared there. Sigma squared. Okay. All right. But I go through the same operations, and this is what I get for the Wald statistic there. Okay. Now, if I go to the score statistic, again, this is just the formula of the score statistic. I don't really know what else to say about it. And so, but you can push yourself through all of the math, and you should come out with this expression, which is what we found over here. Now, I actually think that I just spotted an error here. So I'm not sure if you can see it, but this is not the expression for variance. it's 1 over that. Okay, so let me fix that right now. Okay, so again, you can just work yourself through the math here. Similarly for sigma squared. And now notice that this expression for sigma squared, the score function for sigma squared, is not what we found for the Wald statistic. Okay, whereas for mu it was, right? The statistic for the Wald statistic and the score statistic for mu were equivalent. Okay. And now finally we have the likelihood ratio statistic. In the book it's given like this. Sometimes you see this as -2 times, and then you switch these two terms, but they're equivalent expressions. And so now we're just plugging in the log likelihoods for the two functions, right? For mu naught and mu hat, and you just push through, and you come out again with the same expression for the likelihood ratio statistic. And then when you do it for sigma squared, you come out with yet a third expression for sigma squared. And so now in question 4.9, it says, show that the Wald statistic, score statistic, and the likelihood statistic are equal to one another in this example. Well, we already showed that here for mu, and remember this question is only addressing mu. I am adding on sigma squared, but not for sigma squared. Right? You get 3 different expressions for sigma squared. Okay. Now it turns out though that asymptotically these are equivalent expressions. Okay, so in other words, as n goes to infinity, these all equal one another. So you can kind of already see it here with the Wald statistic and the likelihood statistic, right? You have n here in the numerator and n multiplying everything. Obviously, so as that gets big, these values are going to, be equal. If we just rearrange this guy, which I've done here, we again get n in the numerator, and so as that goes to infinity, it's asymptotically becomes the same as the other two. So, okay, I guess we will call that good.